if you think about what we've seen in the past, we've drawn inferences about a single population mean and about the differences between two population means. And then in this chapter, we thought about drawing inferences about the population variance. And now what we're going to do is we're going to think about the difference between two population variances. But we're not going to use, rather what we're going to use is, that's going to be our target. The ratio of two population variances. And remember, a couple of things we can do in terms of inferential statistics if we know the sampling distribution, our null hypothesis statistical testing, and the 95% CI. I'm only going to deal with null hypothesis statistical testing. So how is this going to work? Well, as was the case when we were comparing the difference between two population means, we're going to have two normal populations. So we're going to assume two normal populations. Got these two underlying populations, and there they are. So we've got population 1 and population 2, and they're both normal. And they've got some sort of a mean, so there's mean 1 and mean 2. And what we're really interested in is the variance, but I'm going to represent it here as the standard deviation. So we got standard deviation 1 and standard deviation 2. And as was the case of the chi-square, we don't really need to worry about the population means. So the techniques that I'm going to go through will work regardless of what the population means are or whether or not they're equal between the two populations. So what we're going to do is, with a sample size of N1, we're going to calculate the variance of that sample, and then we're going to consider the ratio of S squared 1 or sigma squared 1. And then from our second population, we're going to take an individual, and that's going to be based on a sample size of N2. And based on that sample, we're going to calculate S squared 2. And we can think about the relationship, the ratio of S squared 2 over sigma squared 2. And then we take the ratio of these two ratios. So in other words, we put a division line right here. And what that gives us is S squared 1, S squared 2. We do the algebra times sigma squared 2 over sigma squared 1. And remember, that's based on N1 and N2. And that's going to be our F statistic. So we do that once. Take a sample of size N1 from this population, sample of size N2 from this population, calculate all these guys here, come up with this value, and put it on a number line, and then repeat that an infinite number of times. So what we get is all possible values of this statistic F. So if we got all possible values of the statistic F, what have we got? We've got a random variable that we can represent as F. And we can now change it to, and maybe what I should do is go back here for the sake of clarity. And I'm going to change all these guys to little s's. Change all these guys to little s's, so it makes it better. And now when I make my capital F, which represents the random variable, now I'm going to have S squared 1, or S squared 2, sigma squared 2, or sigma squared 1. That's a random variable. Because it's a random variable, it's got a probability density function, and because it's a probability density function of a sample statistic, we can think of it as being a sampling distribution. So if we think about a sampling distribution for the F distribution, so recall that sampling distribution is going to consist of all possible values of F, which is equal to S1 squared, or S2 squared, sigma squared 1, sigma squared 2, when N1 is equal to 5, N2 is equal to 16. In other words, if we consider degrees of freedom, nu, that's going to be 4, and nu, number of degrees of freedom here, is going to be 15. So, we're thinking about the probability, the sampling distribution of F, which is a probability density function. Let's think about the probability density functions we've seen in the past. Again, just as a review, here's our normal distribution. It has the parameters mu and sigma. So we take y, put that into our meat grinder, and what comes out the other end is the probability density function of y. In the case of probability density function for the sampling distribution t, what are our parameters? The only parameter is number of degrees of freedom nu. So we've got our value of nu. We calculate a test statistic t. We put t in here. What comes out is f of t. We consider our chi-square distribution. Similar to the t distribution, it's only got a single parameter, nu, the number of degrees of freedom. There's a number of degrees of freedom. We calculate our chi-square statistic. Now we put our chi-square test statistic into our meat grinder. What comes out is the probability density function of our chi-square distribution. Okay. Now in the case of our F distribution, we've got two parameters, nu2 and nu1, number of degrees of freedom associated with the second population, number of degrees of freedom associated with the first population, and there they are there. What we calculate is our value of the test statistic, F, there it is here, there it is here. So we come out up here, we put in F, and what comes out is this thing which looks a little bit odd. The first F here just stands for function, and the F here means that it's going to be the function associated with the F test statistic. So in terms of how we're going to use these things, recall that we don't use the probability density function in a practical way. What we would do in this course, if there were going to be on the final exam questions about, how do you calculate a chi-square value? How do you actually do null hypothesis statistical testing? You would have tables, but you're actually not going to have to do any such calculations on the final exam for this course. And when you go into 582 and 586, you're not going to use tables. You're going to use the R computing package to calculate those values of probabilities associated with given parameters and given variables that you observe. But anyways, just as a go over, here we've got the chi-square table. And as we saw before, remember their single parameter is nu. And what you've got here are a series of probabilities like this. And what you have in the body of the table are the corresponding values of chi-square. Quite a similar sort of thing to the F table, except now remember you've got two parameters, nu2 and nu1. And so you've got, those are shown here, nu1 and nu2. And what you've got here are the probabilities. So here you have the probabilities here. They represent these sorts of probabilities. And then in the body of the table, what you have is the F value. So again, we can continue on with comparing the chi-square distribution with the F distribution. In both cases, they're skewed. We think about where the mean of the chi-square distribution is. It's associated with whatever the value is of the parameter nu, whereas in the case of the F distribution, here we've got our F distributions. Where is the mean of the F distribution? The mean of the F distribution is equal to nu2 divided by nu2 minus nu1. So, with all that in mind, we can go back and we can actually do null hypothesis statistical testing. So, one of the important concepts of this course is that if you know the sampling distribution, there's a couple of things you can do in terms of drawing inferences about the underlying population, NHST, and 95% CI. I'm not going to go over 95% confidence intervals for F values. I am going to go over null hypothesis statistical testing, but you won't actually have to do these calculations on the final exam. So, null hypothesis testing requires us to have a null hypothesis. And a null hypothesis is that sigma squared 1 and sigma squared 2 are equal. Or another way to look at this is the ratio of sigma squared 1 over sigma squared 2 is equal to 1. So that's a null hypothesis. So what we do is we go out there and we collect two samples. So we've got N1, and that's going to be equal to 5. And sigma squared 1, S squared 1 is going to be equal to 144. From the second population, sample size was equal to 16, and the observed sample variance was going to be equal to 36. So then we calculate our particular value of the test statistic F, and we do that as S squared 1 over S squared 2, sigma squared 2 over sigma squared 1. So, our null hypothesis. Our null hypothesis is that these two are equal. In other words, this equals 1. This value here is 144. This value here is 36. So what we get is that F is equal to the value of 4. Now again, we always come back to this idea that we get a single value of our test statistic. But if we considered all possible values, of S squared 1 over S squared 2, sigma squared 1 over sigma squared 2, where this was equal to 1, and also the N1 was equal to 5, N2 was equal to 16. In other words, U1, number of degrees of freedom was 4, U2, number of degrees of freedom was 15. If we consider all possible values of this, that would be our sampling distribution. So here we've got our sampling distribution. We've got a sampling distribution that looks like that. Something like that. So here's a sampling distribution, all possible values of this. So we think of the value that we observed. The value that we observed was 4. And so if we consider all possible values that we might have gotten for F, with this being true and this being true, that would be shown by this line. So, given all that, if we actually obtained a value of 4.0, what would the probability be? The probability would be very small. And hence what we do is, we realize we've made a mistake somewhere. So where is the place where we made the mistake? Where's the error in all this? The error in all this was assuming that this was equal to 1. So this is our null hypothesis. So we assume that we went awry in assuming this is equal to 1. We reject our null hypothesis in favor of the alternate hypothesis that the ratio was greater than 1. So we'll stop there. This is a review slide. And again, we come back to the idea that if we know the sampling distribution, we can do null hypothesis statistical testing, or we can do a 95% confidence interval. But null hypothesis statistical testing and confidence intervals on what? Well, we've got a variety of different targets. We've got the mean of a single population. We've got the difference between two populations. We've got the variance of a single population, or we've got the ratio between two population variances. So one of the things we ask ourselves, is the population standard deviation? And this SD stands for standard deviation. We've got a bunch of sampling distributions here, and you can see that in the case of mu, or mu2 minus mu1, use a Z distribution when we know the standard deviation of the underlying population. In the more realistic case, where the underlying population variance is unknown, then we estimate the underlying population standard deviation with S instead of sigma, and that requires us, if we're going to draw inferences about either of these two guys, we have to use a t-statistic. Now, obviously, in the case of trying to draw inferences about the population variance or the difference between two population variances, clearly we're not going to know what the population variances are, because that's what we're going to try to draw inferences about. Again, in drawing inferences about a single population variance, we use a chi-square test. Drawing inferences about the ratio of two variances, we use an F-test. Standard error. Let's think first about this guy and this guy. If the underlying populations are normal in either of these two situations, then the sampling distribution here is also going to be normal. Because it's normal, it's going to have a parameter of its own standard deviation, and the standard deviation of a normally distributed sample distribution is referred to as standard error. How about these guys here? Well, they're not exactly normal, but they're essentially normal. They're essentially normal. They're based on a normal. The only difference is that because we've substituted S for sigma, that requires us to use a t-distribution rather than a z-distribution, but essentially these are normal distributions, and so as a consequence, we can think of them as having standard errors. Now, in all these cases, the underlying population is assumed to be normal. But it's only in these four cases that the sampling distribution is normal, or in the case of a t-distribution, essentially normal. We think about the F distribution or the chi-square distribution. Clearly, if we go back and remember the shapes, they were skewed. So in these cases, the sampling distributions were skewed. They're not normal. It wouldn't make any sense to talk about a standard error. Okay, we'll stop there.